Basically, it leverages a whole network of continuously operating reference stations around the ground area for the SBAS. So in this case, that's Australia and New Zealand. It uses the locations at those cause stations and it integrates all of those different measurements to compute corrections for the region. So once all that data is sort of sent through to a processing center, they're uploaded to a satellite and downlinked from that satellite to the end users.
Welcome to the Mapscaping Podcast. My name is Daniel and this is a podcast for the geospatial community. Today on the show I'm talking to Chris Marshall. He is a positioning engineer at a company called Frontier SI and they have built a satellite-based augmentation system. So in case you're wondering what that is, don't worry, we're going to talk about it in detail during this episode, but just so you know, during the episode we refer to it as an SBAS system. I'll join you on the other side of the conversation with a few final thoughts about this episode. Okay, let's go. Welcome to the podcast, Chris. Thank you very much for taking the time to talk with me today. It's much appreciated. We're going to be talking about a system called SBAS, and yeah, I think before we dive into what that actually means, what that is, I think it'd be really interesting just to hear a little bit about your journey, how you got involved with geospatial.
Thanks, Daniel. So, happy to be here. So my journey with geospatial, it all started at uni for me. I originally didn't really have much familiarity with the spatial field. I didn't really know what it was, to be honest. I think, like a lot of people, you just sort of discover this along the way somewhere. I actually started at university doing mechatronics engineering, mechanical, electrical. Somewhere through that process, I came across a subject that was called applications of GIS. Turns out there's lots of applications for GIS. And since then, the whole spatial world sort of opened up in front of me. And since then, it's kind of been a whirlwind journey the last few years. I have basically been lucky enough to spend the last 2 or 3 years working on satellite-delivered SBAS. It's a long story about how it all particularly happened, but suffice to say, started through university, did a master's research project, which ended up being at the CRCSI, now known as Frontier SI, where I now work as a positioning engineer. They've been working for the last few years on the SBAS project. And yeah, the rest is sort of current history.
Maybe we should start with clarifying what SBAS is. It's an acronym. Can you just explain to the listeners what the acronym means?
Sure. So SBAS stands for Satellite-Based Augmentation System. What that is a augmentation to standard GPS or GNSS signals. So roughly speaking, it's a service that can improve the quality of positioning from GPS from multiple meters down to sub-meter level.
This sounds amazing. And it is amazing because we've talked about this before. But maybe, just maybe, we should take the listeners along the journey here. How does it do that? How does this system work?
So SBAS uses similar technologies to other high-precision correction services that people might be familiar with from the uses in industry. Basically, it leverages a whole network of continuously operating reference stations around the ground area for the SBAS. So in this case, that's Australia and New Zealand. It uses the locations at those cause stations and it integrates all of those different measurements to compute corrections for the region. So once all that data is sort of sent through to a processing center, they're uploaded to a satellite and downlinked from that satellite to the end users. So at the end of the day, the only thing the end user needs to see is that satellite signal alongside the usual GPS or GNSS observations, and you can get to corrected GPS signals.
Would it be fair to describe this as a base station in the sky, or is that too simple of a description?
Honestly, that's a great way of thinking about it. A DGPS station in the sky is more or less what the SBAS is. The same technology could have been applied from, ground-based stations. There's a few notable advantages to it being in the sky, of course. With the satellite being geostationary, it sits above Australia and New Zealand at a certain elevation angle all of the time. So as long as you maintain a sky view, you'll be able to see this satellite.
Could you talk about some of those sort of advantages of being in the sky again? But I think we kind of brushed over it a little bit there. Why couldn't we deliver the same service like via radio signals, for example, from a ground-based system?
Oh, you absolutely could. So the correction services, there's a whole host of them available, depending on sort of what your accuracy requirements are, what your technology will allow you to do. There's different ways you can go about getting high precision signals. If you're within an area that has mobile coverage, you can go a step above something like SBAS and you can start using real-time kinematic corrections directly from a cause station. There's a limitation there, though, that'll only work while you still have a data connection available to you, which is, for most places in Australia, limited to the mobile networks. So if you run out of 3G or 4G data, you can't get that uplink or that downlink in two directions. SBAS is great because it's just a single direction. As long as you can see that satellite, you don't need a data connection, you don't need anything else, you just need an antenna and a GPS that can pick up the signals. So SBAS means for Australia and New Zealand that if you're anywhere on both countries or in the maritime zones and you can see that satellite, you can get higher precision in your GPS.
And what does that mean for the user? Do I need something, a special receiver? Do I need software? Do I need to buy any extra hardware to be able to receive and benefit from this extra signal?
So there's a short answer and a long answer there. Short answer is that no, you won't actually need special hardware. The most basic implementation of the SBAS uses the same frequency as your standard GPS satellites do. So it picks the SBAS satellite up as just another satellite to include in its sort of computations. If you're talking about some of the more advanced uses of SBAS, and the implementation that we had in Australia and New Zealand was a little bit forward thinking. We were trying out some new stuff with it. So the newer signals and the newer combinations of signals will require some different hardware, but on the basic level, SBAS can be picked up by very, very simple hardware. It doesn't have to cost a lot. It can be existing. A lot of people have receivers that currently be in use that will be SBAS compatible. You might just need a software or a firmware update to get it working.
Okay, so a very basic use case for me would be I'm walking around somewhere with my mobile phone. It obviously can receive a GPS signal. It'll pick up this geostationary satellite, this SBAS satellite, if I'm in the correct sort of geographic area. And I won't notice anything as a user, right? I'll just notice perhaps that my positioning is more correct, that if I was to track myself over a long period of time, perhaps I wouldn't bounce around so much. Is that sort of a fair understanding of what's happening?
Yeah, that's a good way of thinking about it. So smartphones are definitely where this is all kind of leading to in the future. I think there's a couple limitations with using SBAS on a smartphone at the current time, but there is a bunch of research being done right now to try and make that a reality. Absolutely. There's a few benefits, honestly. It's not just positioning accuracy, it's also reliability, availability. So you get more reliable signals. You can see the signals more of the time, and the result you'll get from the signals will more often be correct or more correct than it would be if you were using augmented GPS. So depending on what your operational use case is, or depending on what you're trying to do with GPS, there's sort of a set of trade-offs there. Do you need the highest possible accuracy? Do you need the highest possible integrity? Do you need to know that there is always some positioning coming through your signal? It really does depend on sort of what industry you're in and how you are using the positioning data in the first place. But that said, SBAS provides a whole host of those benefits. The most simple one, of course, being accuracy. So you will get a more precise location. If you're looking at the map, it won't put you on the opposite side of the road or through a building as often.
I think you mentioned reliability there. I just need to make sure that I'm understanding this correctly. We're not talking about a stronger signal here, are we? We're talking about an extra signal that our receiver is going to pick up and use that to create a more, in its most basic use form, a more accurate position.
Absolutely, absolutely. So just as an example, if you can imagine you're in an urban area, potentially an urban canyon, as they're called, where there's buildings on both sides of you, and your sky view is limited to sort of a narrow corridor through these buildings. In those circumstances, GPS generally struggles quite a lot. The accuracy that you can get out of the system there is dependent on the geometry of the satellites that you're observing all around you. If the geometry of those satellites is limited to this sort of narrow strip of the sky, you can't resolve your position anywhere near as well. You end up with big errors, and people who've tried to use a GPS in severely urban areas will often find it's jumping over the place hundreds of meters sometimes, pushing you inside buildings, 10 stories in the air, all kinds of really, really weird things, mostly due to errors like multipath. With SBAS, these are still factors. Multipath is still going to be an issue, but if you can correct for common error sources, you can get a more reliable service, even with fewer GPS satellites visible to your receivers. It's not going to be a silver bullet. It's not going to fix all of the issues that you might have for reception, but if you're under Skyview that can see the SBAS satellite, you will get a better result than you would otherwise.
I want to sort of talk about this geostationary SBAS satellite just for a second here, and then move on to the actual system and give the listeners an understanding of how the system is built up, how the data gets to the satellite. Well, why is a geostationary satellite a good choice for this? Because, GPS as we know it is a constellation of satellites that is constantly moving around. Is this something we can just add to existing constellations? Or why do we need a geostationary satellite?
That's a great question, actually. So it comes down to the fact that the corrections for the SBAS are regional in nature. So this SBAS is being developed for Australia and New Zealand as a footprint. That means that we're using data from within Australia and New Zealand cause sites to determine those corrections. There's similar SBAS systems actually deployed elsewhere in the world. The first one was the US WAS system, Wide Area Augmentation System. It's been up for over a decade at this point. That's the initial SBAS that was delivered in the world, and that was purely for the North American region. Since then, there's been a few other ones developed. There's some under development around the world, but I think there's a European one. There is a Russian one in development. I believe there's currently an SBAS under development in India, South Korea, a few other places. I'm probably forgetting a few here, but there is definitely some notable SBAS systems globally, and each of them will rely on a different set of input cause stations to get those corrections for the region. So there's potentially ways that in the future these sort of technologies can be delivered globally, but in the current form of the SBAS that we're seeing deployed currently in the world, it is tied to a certain particular region.
So maybe we could talk about the rest of the system now. We understand why we're using a geostationary satellite, and we've sort of skirted around a little bit about the data that the satellite uses. Could you explain what the journey looks like for this data? So we talked about a system of base stations collecting these constant positions and making corrections based on that. How do they get to the satellite?
Absolutely. I mean, it all starts at the satellites. The satellites are always putting out their signals. The ground stations, as I mentioned before, continuously operating reference stations throughout the whole region, Australia, New Zealand in this case, they receive all of the satellites. They're basically a very good quality GPS receiver themselves. They pick up all of these signals and they locate themselves based on what they can see. So these core sites determine their own position, and they also know for a fact their last surveyed position to a high degree of accuracy. Based on the difference from the computer position at each cause site versus their known location from survey across the entire network, you can work out sort of a factor of how much error is being brought into the system from transmission from the satellite down to the ground segment. So mostly that's correcting for ionospheric errors. So once the signals are all picked up at the core sites, they use that difference in position to work out the ionospheric error, and they can then send that through to a ground processing station. That station takes all that data and puts out corrections for the entire SBAS region based on where in that sort of that region you might be. So the more core sites across the region, sort of the better, but there's sort of a minimum number, I think, that we have well more than that in Australia and New Zealand. Some regions in the world, it's a struggle to get enough cause sites up to get the data through to build an SBAS, but we're lucky there's a lot of core sites across the country, and they're used for all manner of surveying and precise positioning tasks. So we're already a bit mature in that space, and it made it very simple to transition those data streams forward and use them for SBAS purposes. So yeah, there's the ground processing station, computes the corrections. It's then sent to an uplink center. The uplink center's only job is to talk to the satellite, the geostationary satellite in this instance. So the communications uplink happens. It's sent those corrections messages, which is then immediately downlinked from that geostationary satellite and just broadcast on the same frequencies as the standard GPS.
Thank you very much for walking us through that process. I think I'm going to have to try and draw an infographic of this as well, so I can just kind of visualize it in my own mind. But I really appreciate that. Does this replace RTK?
No, I don't think this will replace RTK. However, it can be useful in circumstances which traditionally would have been the job of RTK. There's a lot of RTK use cases where you really do need that sort of 3 to 5 centimeter accuracy and precision. SBAS really can't get there yet. We can, however, get down to a decimeter level with one of the new signals that we've been trialing out, which is almost good enough. And depending on your use case, there's going to be circumstances when the simplicity of the system not requiring two-way communications and still having that sort of decimeter level accuracy will be really, really beneficial.
Could you explain to me why, how this difference in accuracy comes about? Because I'm assuming that RTK is based on the same sort of network of base stations, is it not? The same network that is ultimately supplying data to the SBAS.
Absolutely. So yeah, there is multiple ways you can do RTK. There's networked RTK, which does use a network of these core stations, as you mentioned. But the simplest way of doing RTK is just using single base station RTK, in which you connect up to the local cores that you're nearby to, and you take a direct feed from there for corrections data. Doing so, you'll get to that 3-5 centimeter level, but you have also an additional factor that is based on the distance from you to the base station. So if you're 10 kilometers from the base station, you'll get pretty decent 3 to 5, sometimes, a little bit more level accuracy, 3 to 5 centimeters, sorry. But as you go out to, 100 kilometers, 120, 150 kilometers from that core site, that accuracy that you can achieve will start to taper off and will slowly degrade, which is not a factor with SBAS. You can pick up the same level of accuracy anywhere in the country or the maritime zones.
That's amazing. I just need to make sure I understand that. So I can expect the same level of accuracy anywhere within that sort of footprint of the SBAS. It doesn't change. It's not like, okay, I'm closer to a base station here and therefore I'll be a little bit more accurate.
Absolutely. It's purely dependent on your satellite observation conditions. How well can you see the sky? How good is your receiver? How good is the rest of your hardware? And if you have all the pieces in place, you'll get corrected data through and you'll get down to the correct level of accuracy. So yeah, the SBAS kind of decouples from the core's infrastructure directly. It allows you to kind of leverage it without needing to manage the core side itself.
I think this is absolutely amazing because for me anyway, the magic here is it just happens, right? If I have the correct technology, again, in my phone, for example, then I don't have to do anything, right? It'll just happen. I'll just get a more precise position of where I am. Perhaps you could talk us through some of the use cases for this. So Australia, New Zealand are big agricultural countries. I can see a huge future for this in terms of precision agriculture, but maybe you've got some interesting use cases you could share with us?
Absolutely. In fact, use cases for SBAS has kind of been a focus of myself and Frontier SI over the last sort of 3 or 4 years. There's been a huge body of work we did around the SBAS, known as the SBAS testbed, which was specifically looking at different use cases for the SBAS and trying to kind of put them into different organizations, different sectors of industry, and then trying to kind of quantify what those benefits would be in the future. So, in fact, there's been a lot of work done to sort of look at how these could be applied in various industries. The biggest ones, I think, are, as you mentioned, agriculture. I think there was 4 sectors from memory that ended up with an over $1 billion valuation, and that's projected over the next 30 years. And one of those was the agriculture sector. Specifically, I think there was $820 million projected in feed and fertilizer savings for farmers due to the enhanced pasture utilization that you can get from SBAS-enabled virtual fencing. So virtual fencing is a fascinating concept as far as I'm concerned. There's different ways you can do it. The idea of having a virtual line or a virtual boundary within which things are held can be applied to many sectors, construction, resources, agriculture, of course. But one thing that I found was absolutely fascinating. One of the things we trialed in the SBAS testbed, they were trying SBAS-enabled collars on livestock. So they had some cows lined up with GPS receivers on their necks, and they had the ability to draw a line across this paddock. And if the cows would approach that line, they would get a sound alarm. They would kind of just buzz at them and beep a little bit. And they didn't like it when they would beep, but it wasn't, damaging them or any way. It wasn't hurting them or anything. But they would learn over time that if I don't go over there, it won't beep at me. So what that sort of forms in behaviors, if you have enough of the herd wearing these collars, they just won't go to a particular region. The end goal with this, of course, is to try and get all your cows lined up along a field and slowly move that line forwards. So you can imagine sort of a large lawnmower effect of all your cows grazing where you want them to be over time. And SBAS virtual fencing can kind of potentially get you there. So that's just one application.
That's amazing. That's a use case I definitely would have thought of. But I can see that, if you removed all of the real fences, that would sort of open up things too for automated or autonomous vehicles to come in and do a lot of the other farm work, I'm assuming. And I'm imagining they could also, in the future, make use of the SBAS system.
Absolutely. There's definitely within the horticulture and broadacre sectors, there's a lot of spraying, seeding, spreading operations that are currently, if they're done with precision GPS, they're usually done with RTK. We're finding that the SBAS can be good enough for some tasks. There's definitely going to be, with every industry, there's going to be some use cases where you do need that highest level of accuracy in which you'll be looking at an RTK solution. However, for some of these jobs, it's good enough to use SBAS, specifically areas when your absolute accuracy isn't so much of an issue, more your pass-to-pass accuracy. So A farmer might not worry that if they mark a point in their paddock, that they come back in 4 or 5 years time, that exact point is exactly where they took it to be. They're more worried that if I drive my tractor down this row now and I come back in 20 minutes and I try and drive the exact same row aided by GPS, will I go to the same place or will it have moved? And that's definitely something that is slightly simpler than overall absolute accuracy, and SBAS is good enough in many of those circumstances.
So when people hear about systems like this, and people like me, definitely, we tend to get a little bit excited and like, this is the silver bullet, it's going to save the world, it's going to solve all our problems. And I think you've done a really great job of sort of walking us through what it is, how it works, and some potential use cases of it. But maybe you could tell us about times when this is not the right solution.
Yeah, absolutely. As I mentioned before, I mean, SBAS has its advantages over, standalone GNSS. It's got some advantages over RTK corrections, but there is no substitution for that level of accuracy that you can achieve with a networked RTK solution, or otherwise being close to a core station using a single RTK solution. When you need that 3 to 5 centimeter accuracy, you should still be using 3 to 5 centimeter accuracy. In fact, it's really great if you happen to live in Australia or New Zealand. Both geospatial agencies provide free data streams to those services. So Geoscience Australia, through the AusCores service, will provide you a direct feed to your local core site. So if you have a compatible receiver, you can get free corrections in that 3 to 5 centimeter level. And similarly, in New Zealand, they provide a similar service. So if you're in the market for 3 to 5 centimeter use, there's nothing stopping you from going out and doing that at fairly low cost already. The additional costs usually come in the equipment. RTK equipment's a little bit more difficult to get your hands on than something that can run SBAS.
What does the future of this look like? Is this the end game now? So is it just a matter of having more core stations, more of these base stations, building a bigger network and improving accuracy that way? Or are there other things we can do in terms of augmenting a satellite-based system like this?
Right, yeah. So there's actually a few different next steps here. It might be easier to take a few steps back, honestly, and talk about sort of how we got here. Roughly speaking, the SBAS is underway and it's kind of on its way in its current implementation, but we've also been testing it during this period of time. As I mentioned before, there's this SBAS testbed that actually is happened between 2017 and 2019 and was designed specifically to trial all these different use cases in all these different industry sectors. Following that sort of testbed run by Frontier SI with a whole bunch of industry partners, specifically Geoscience Australia, Land Information New Zealand, and of course the technology partners who help run the service, we ended up demonstrating through an economic benefits analysis there'd be $7.6 billion in benefit from this service over 30 years, which is significant enough to actually prompt the Australian New Zealand governments to invest in the service. So the current state we're at right now is that it's on its way. It's going to be coming at some point in the near future. You're going to have to sign up for Geoscience Australia's newsletters if you want official word on when and how exactly. But suffice to say, it's currently under development and that it'll be coming in the near future. So with that in mind, there's no current clarity about what the final implementation will look like, but we can make some educated guesses based on the technologies we did test over the last few years. Within that, there is your standard L1 SBAS service we've been talking about. It's the simplest one to pick up. It's the most compatible with the widest range of equipment. However, there's also these more future-focused solutions. We've got a dual-frequency multi-constellation SBAS, which uses multiple satellite constellations and corrects both of them. Two major constellations being the GPS and the Galileo constellation, and corrects both of those, theoretically providing a slightly higher degree of accuracy, but most importantly, a higher level of integrity than a standard SBAS solution. And this PPP service, which can get down to that decimeter level, notably after a convergence period of time. So there's sort of trade-offs with each of these services. And those, I feel that the key thing with this whole program, of course, is that they're all provided for free. The end goal of this is to provide a service which can be picked up by anyone in Australia or New Zealand and applied to whatever operational use case you have without any real barriers to entry. All that kind of harkens back to the original implementation of this technology. SBAS was designed for aviation use. As an inherently aviation technology, you can't be charging people for access to this. In the sense we're trying to allow people to improve their own safety, improve their own positioning quality. And if you're trying to land on a runway and your SBAS needed a login all of a sudden, you'd be in real trouble. So as a result of that, all these services are provided for free and openly to anyone who needs it. So to answer your question, these form part of sort of a precise positioning ecosystem. The SBAS has its own place. RTK corrections still have their place. But by making all of these things available and more accessible to all sectors and anyone who wishes to use them within the country, we aim to basically uplift that spatial capability throughout the countries and allow people to do more, people to get the technology in their hands and just try out new things and see what works. Because ultimately, that's where the real innovation comes from. It's your average people getting their hands on something shiny and new, getting excited about it and trying it out and seeing what happens.
I think this is really incredible because what I'm hearing you say is that Australia and New Zealand have recognised precise positioning as like a national good, something they want to provide for free because it'll improve people's safety, because it'll have these incredible economic benefits. And I guess in terms of GPS, for example, we've seen this, right? Like how many billions of dollars have been in value have been created based on being able to locate people accurately anywhere.
Oh yeah, it's significant. There's entire industries built around location services. I mean, there's multiple sides of this. When people talk about, locations and data collection, there's always this privacy underlay there. People are concerned, oh, if you're tracking me to a high degree of accuracy, does that mean that everyone knows where I am all the time to a better degree of accuracy? That sort of underlying data sovereignty, privacy, all that stuff is still an issue and it will continue to be an issue in the future. But I think it's worth noting that the benefits that you can accrue from knowing where things are to a high degree of accuracy far outstrip sort of the immediate concern that I think many people have for if you know where I am on this side of the street versus a couple meters away. So privacy is always going to be a concern, but security is definitely something that is inherent to an SBAS system, specifically if we're talking for aviation use, and that is where the goal is in the future. The SBAS is ultimately slated for integration into the civil aviation standards. It's already defined in the standards that are used internationally, there's been SBAS systems in the US for over a decade, as I mentioned. They use it routinely for aviation use over there. But before it can be used reliably for those purposes, we need to ensure that there is secure ground stations that can provide the SBAS. There's sort of a few extra things that need to be done over the next few years. So while some of the early indications for SBAS system coming back online in Australia projected somewhere around 2021 or so for the return of SBAS signals for ground users, the aviation use case might not be around until 2025 or so. And that's purely to allow that sort of security to be developed, the sort of the background ground infrastructure to be built up and ensure that the system is as reliable as it can be. Ultimately, in aviation, they're not concerned about centimeters of accuracy. They're more worried about landing a plane on a runway. So with that in mind, the major use case of this SBAS system is not even the accuracy there. It's fascinating to think that there's a massive benefit from SBAS that has nothing to do with the accuracy, but the integrity of the system and the availability of the system are definitely the key focuses there. I think you can imagine in a plane, you're not worried so much about 1 or 2 meters left or right, but you are worried if you're coming in for approach and your system drops out, or you're coming in for an approach and your system suddenly starts telling you unreliable information. And those are the sort of things that really need to be verified. So there's very strict standards for these things, and a very, very high level of certainty is required for aviation use case. I could dive into that a lot more. My master's thesis at university was looking specifically at the use of SBAS in civil aviation and whether or not the SBAS testbed implementation in Australia and New Zealand would meet the international civil aviation standards. So I'll stop talking about that. But
I think you've done a really amazing job. It's a technical subject. You've done an incredible job of sort of walking us through it, what it is, what it looks like, how it works, the benefits, some of the use cases. So I've really appreciated your time and I've enjoyed the conversation. But before I let you go, where can the listeners go if they want to reach out to you, if they want to learn more about what you're doing and what you're working on?
Absolutely. So, if you're looking for any more information on the SBAS, sort of the test bed or any of the work that's been done over the last few years, I'd suggest you just jump on the Frontier SI website. There's sort of a SBAS subsection or a SBAS central page there, which contains a whole bunch of different information. There's a bunch of reports that we released as part of the SBAS testbed and subsequent demonstration projects. There's some cross links to Geoscience Australia and Land Information New Zealand, both of which have been doing really great work in the space. Also, I should mention that there's actually, if you are yourself a positioning user from Australia or New Zealand and you're excited about these upcoming signals, we're actually doing an outreach program at the moment. We're looking to hear from any positioning users from Australia and New Zealand, specifically through a sort of questionnaire. You can sign up for that questionnaire online, and then at some point there'll be some sort of questionnaires going out to people, specifically to try and understand a bit more about how you use positioning data, what your needs are, what your requirements are, so we can help tailor these services to meet the needs of all sectors of industry. So if you are a positioning user, definitely look out online. There's Quest for Insights going out that's available on the Geoscience Australia website. Look for some of those news articles, or you can have a look at Positioning Insights. Otherwise, come on Frontier OSI, have a look at all the documentation we've got available. And if you have any questions about SBAS or you'd like to learn a bit more about how you could use it for your organization, feel free to reach out to Frontier OSI directly. Very, very happy to have a conversation with anyone anytime. We'll have a chat about what exactly it is you're trying to do with SBAS, and we'll get you started.
Thanks very much, Chris. I really appreciate your time.
Thank you very much, Daniel. Thanks for having me. It's been great.
I really hope you enjoyed that conversation with Chris. I hope you enjoyed learning about satellite-based augmentation systems. I realize the name sounds a bit intimidating, but when you think about the way it actually works from an end user perspective, it's incredible in its simplicity. It's just going to be perceived as another satellite, another signal from space that's going to dramatically increase the accuracy and precision of your ability to locate yourself or locate your device. Back in 2019, I recorded an episode where the topic of conversation was around smartphones and their role in precise geolocation and what that would look like in the future. And during the episode, we talked a little bit about positioning as a service. So I will link to that episode in the show notes if you want to have a look at it. And I think the difference between that episode and what we've just been talking about now is, so positioning as a service is obviously a pay-to-play thing. But this SBAS, this feels much more like positioning as infrastructure. So I guess like a lot of you, when I think about infrastructure, some of the first things that pop into my mind are roads, for example, the water pipes that bring water into my house, the internet. And I think that the value proposition there is really clear. Without the road, I can't transport myself or my goods to certain places. Without the internet, I mean, we all understand what the internet does. Without the water company, without the water transportation system, I can't drink. It's no longer viable to live where I live because I'm not necessarily beside a reliable, clean water source. But I think positioning as infrastructure, the value proposition is simply, I'm going to give you a common understanding of talking about location. That's it. And by improving that, we're just saying, okay, I'm going to make it more precise and more accurate. And yet the value created by that, as Chris mentioned in one of the reports there, was $7.6 billion over the next 30 years. You know, a lot can change in 30 years. We have no clue what kind of services and products are going to be based upon this or possible because of this. I think too, it's really interesting to think about what this is going to mean for data collection, right? So a dot in space, even a very accurate, precisely located dot in space, has no real value. But if we start using the ability to create accurate, precise dots in space to capture features, to capture data, to update data sets like OpenStreetMap, that then go on to propagate into other data sets and create other information. I guess my point here is that it's really difficult to understand how much value is actually going to be created from this. It's one thing to talk about real-time services, so here and now decisions being based on better, more accurate, more precise information, but the knock-on effect of better data over 30 years, that would be really interesting to know. So Chris was generous enough to share a whole bunch of interesting links to amazing resources. I will put those in the show notes. As Chris mentioned, he's looking for people to help them out, sort of make suggestions. What can the system be used for? How can they improve it? If you live in New Zealand and Australia and think that this system might add value to you in some way, shape or form, I would really appreciate it if you would take the time to connect with Chris and help him out there. With regards to the podcast, I am taking a break for the next few weeks, so I will be back again in the new year with a whole bunch of new episodes. So please be patient, please stick around. There's a whole back catalogue to cruise through if you haven't done so already. And as always, you're more than welcome to reach out to me. So my name is Daniel. I'm easy to find on social media. Search for Daniel Mapscaping, podcast host, something like that. And I'm more than happy to connect with you on LinkedIn. And I'm wishing you all the best holiday season. And I'm really looking forward to producing this podcast again in the new year. Okay, that's it from me. We'll talk again next year. Bye.